I believe this is the last section in Chapter 3, which must mean we have a test coming up next week. Excellent. I'm glad you're up on the schedule. If I didn't have my calendars, I wouldn't know what was going on at all. So this is on derivatives of trig functions. Okay, we've done a lot with polynomials. We've done some with roots. We haven't done exponentials or logarithms yet. We will. That's coming, but not in this unit. So today we're adding on the derivatives of trig functions. So let's go to our calculators, and you were supposed to graph sine of x and do it in bold. So we can do over here. If you happen to have, neither of you do, I was going to say, if you have the color edition of the TI, you don't have to. And then over here, we're going to graph the derivative, which is, what is that, math 8? So the derivative with respect to x of, you can type sine of x in there, but you know you don't have to. If you do alpha trace, there's y1, and you can just put that in. You don't have to recopy the whole thing. It's not such a big deal on this one because it's just sine, but if that first equation was something really ucky, right, then that saves you some time. And because this is trig, do you guys know that this has a zoom trig? Never used it before, have you?
No.
So there's sine, and here comes its derivative. And it takes it a while for the derivative to be graphed, because it's having to think about every single point. But what graph does that second thinner graph look like? It looks like cosine. And in fact, it is cosine. The derivative of sine is cosine. That's, honestly, for me, I remember the first time I learned that, I was like, that's unexpected. But it kind of makes sense. If you look at this, the slope of the sine curve at 0, 0 looks like it's about 1. The slope of the sine curve here is 0. The slope of the sine curve here is -1. And if you just stitch that together, you're like, oh, yeah, that's cosine. But it's very cool that the derivative of sine is cosine. We can also, now, if you know that, you might assume that the derivative of cosine is sine. It is not, but it's not far from it. So if we go back to this and change this one to cosine, and we graph it now, so here's cosine, which it graphs very quickly, and here's its derivative. Like, oh, it kind of looks like sine, but it's going the wrong direction. It's flipped over. It turns out that the derivative of cosine is the opposite of sine. It's negative sine x. We'll write that down, or it's written in your notes someplace. But I do want to take you through this derivation real quickly. You do not have to know this derivation. Just as math students, you should see proofs of things most of the time. Not all the time, because sometimes it doesn't help. But you should see these. So, in order to do this, you need to know these two limits. This one we know. We've done this one a bunch, right? The limit as h goes to 0 of sine of h over h is 1. The other one that you need to know is one we haven't used very often, is the limit as h goes to 0 of cosine of h minus 1 over h actually goes to 0. So using the definition of a derivative, the derivative with respect to x of sine of x will be the limit as h goes to 0 of sine of x plus h minus sine of x over h. That's just the difference quotient, right? You guys are good at that at this point? All right. So then, from here, you have to know the sum identity. I don't know it. I can never remember the sum and difference identities. Usually with a little bit of brushing off, I'm like, oh, yeah. But this is not something that comes up often enough to where I am going to expect you to memorize it. I expect you to know the Pythagorean identities, that sine squared plus cosine squared is equal to 1, and that tangent squared x plus 1 is equal to secant squared x. Those, most of the rest of them, you don't need to know at this point. Okay? So sine of x plus h is equal to sine of x times cosine h plus cosine x times sine of h. And I'm just keeping the sine of x. Here's where you start getting tricky. What we're going to do is we're going to factor a sine of x out of this term and this term. If I factor a sine out of those two, I get sine of x times cosine of h minus 1 all over h, plus I still have this middle term, cosine x sine h over h. So I've done two things there. I've factored and I've split it into two different fractions. So now what I'm going to do is factor the sine x all the way out of that so that it's sine of x times all of the rest of this. The cosine h minus 1 over h. And here I'm going to factor the cosine out so that I've got cosine of x times sine of h over h. As h goes to 0, this term, or this factor, goes to 0. So I've got sine of x times 0, and this one goes to 1, so I've got cosine of x times 1. And we've proved now that the derivative of sine of x is equal to cosine of x. You were pretty well convinced just by looking at the graph, right? It's pretty convincing. I don't know that the proof helps convince you anymore, but this is the kind of stuff that goes on when you do mathematical proofs. A lot of times you have to know things like, oh, I need to know these special limits. Oh, I need to know this property from pre-cal. If you ever take an analysis class, this is where you prove all the stuff in calculus. You got to know all that stuff. Fortunately, we don't need it. You could do a similar thing to prove that the derivative of cosine of x is equal to negative sine x. So these need to be things that you have memorized. I don't really worry about people memorizing these all that much because they're pretty straightforward. People tend to be pretty good at having them memorized. So, well, now we can do problems where the product rule has to be used. So far, with almost everything that we've done, you could get away with not using the product rule because you could multiply things out and get some, it might be ugly, but you could get some sort of a polynomial. Now, with this, not so much, because I've got a polynomial function times a trig function. So when I'm taking the derivative, I'm going to have to use the product rule, which, the way I do it at least, I keep the first factor, x squared, times the derivative of the second factor, the derivative of sine being cosine, so that'll be cosine of x, plus the second factor times the derivative of the first, which would be 2x. You're certainly welcome to leave it like that. I will say on the AP exam, they're probably going to write it with the polynomials in front because they were to start with. Not a big deal. They also may factor them. So the only thing that can be factored out of this is an x. So you could have x times x cosine x plus 2 sine x. You'll see that sometimes as well. Just don't be freaked out by the way that they'll simplify things. As far as the test for this class is concerned, unless it's a multiple choice question, feel free to leave it like this. I don't think doing either of the other things really simplifies your answer. Okay? All right, let's do this one. Here, we're going to have to use the quotient rule. We're going to take the derivative of u with respect to t, so that'll be du dt is equal to the denominator, 1 minus sine of x, or sine of t, times the derivative of the numerator. The derivative of cosine is, so this will be negative sine of t minus the numerator, cosine of t, times the derivative of the denominator. Well, the derivative of the sine of t will be cosine, so I'll have negative cosine of t. All over 1 minus sine of t, quantity squared. I do expect that you'll simplify these, because this can be simplified quite a bit. But if this was and you're never going to be asked just this on the AP exam, but if you were on a free response, this would be plenty. Okay, you don't need to simplify on the AP exam, but we will for this. So I'm going to have negative sine of t times 1 is negative sine of t. Negative sine of t times negative sine of t is positive sine squared of t. And negative cosine t times negative cosine t is positive cosine squared t. All over 1 minus sine of t, quantity squared. And here's where I said you need to know those Pythagorean identities. Sine squared plus cosine squared is what? 1. So my numerator is now 1 minus sine of t over 1 minus sine of t, quantity squared, is equal to 1 over 1 minus sine of t. So you can see sometimes these are going to simplify quite a lot. All right, let's move on. Okay, so again, this is an example from physics. You probably have done one like this. Have you done something with like a hanging weight on a spring where it oscillates back and forth at some point?
Probably, yeah.
Probably, but you've slept since then?
Yeah.
Okay. So we have a weight hanging from a spring, and it's stretched from its at-rest position, y equals 0, 6 units. So it's stretched down to y equals negative 6. Then released at time t equals 0, so that its position is given by y is equal to negative 6 cosine of t for times between 0 and 15 seconds. What are the velocity and acceleration at time t, and describe the motion? All right, so let's start by finding the velocity and the acceleration. So v of t, so I'll keep the negative 6 times the derivative of cosine of t, which is negative sine t. So this is 6 sine of t. And the acceleration will be the derivative of that. The derivative of 6 sine of t will be 6 cosine of t. So we'll do this just like the one we were going over on the homework from last night. So the weight starts at time t is equal to 0 at y equals negative 6, we know it's going to move upwards. The question is, well, how long does it move upwards? Well, it's going to move upwards until the velocity is 0 again. So I need to figure out, well, where is 6 sine of t equal to 0? So that's going to be wherever sine of t is equal to 0. So that's at t is equal to 0 and pi and 2 pi. And let's see, this goes until time 15. Wow, I should have just gone until like time 10 or something. Let's see, that's going to be up to almost, but not including 5 pi. So 3 pi and 4 pi. So it starts at this position, then moves upward until it reaches its maximum height. And that's going to happen at time pi. Let's see, negative 6 times cosine of pi. Cosine of pi is? Negative 1 times negative 6 is 6. At t is equal to pi. All right, so what's going to happen then? Well, then it's going to move downwards. Then downwards until it reaches its minimum height. Y equals negative 6 at time t equals 2 pi. This pattern then repeats. I don't want to write it all out. Until t is equal to 15. Now, if you've ever actually done an experiment like this, what happens is that you pull it down, to negative 6, and it goes up, goes down, but what happens pretty quickly is it starts going less and less in each direction, right? Okay, pardon?
So yes.
And I don't remember if it's the spring that causes that, or if it's wind resistance, or if it's, I don't know what it is. It's probably gravity overcomes the force of the spring at some point. So that's partly why they only had this go for a few seconds. Okay, because pretty quickly it stops doing that. The oscillations get smaller and smaller. Okay, questions about this? So similar to what you were doing on last night's, just with trig. All right, so if you know the derivative of sine and cosine, you can figure out all the other ones really quickly without a horrible proof like the one that we did a minute ago. So We know that tangent is equal to sine over cosine, right? Again, that's one I expect you to know. Let's find the derivative of tangent of x. So, the derivative with respect to x of tangent of x will be the derivative with respect to x of sine of x over cosine of x. And how can we take the derivative of that? Yeah, use the quotient rule. So that'll be cosine x times the derivative of sine x, which is cosine x, minus the numerator, sine of x, times the derivative of the denominator, which will be negative sine x, all over cosine of x squared. Now then my numerator becomes cosine squared x plus sine squared x over cosine squared x. What does that numerator simplify to?
1.
1. So this is 1 over cosine squared x. And you could leave it that way, but mathematicians, being the lazy people that they are like, oh, that's too much. What's 1 over cosine? Secant. This is secant squared of x. The derivative with respect to x of tangent of x is secant squared of x. It's pretty cool how simple the derivative is. It's like, you feel like it could be something a lot more complicated, but it's really not. The derivative of tangent is secant squared. I'm not going to go through all of these, but we could. If we did, we would find that the derivative of cotangent is negative cosecant squared. Derivative of secant is secant times tangent, and the derivative of cosecant is negative cosecant cotangent. So again, these would be things that you really need to have memorized. I'm going to point out two things that I think may help you with the memorizing. First of all, notice the derivative of anything, if we add the other two that we did at the beginning, the derivative of sine of x is cosine of x, and the derivative of cosine of x is the opposite of sine of x. Which ones have a derivative that is negative? All the cofunctions. Cosine, cotangent, cosecant. All the cofunctions have derivatives that are negative. Okay? The other thing that I remember, and I don't know if this will help you, but once I thought of it, it helped me, is with the secants and tangents, it's easy to kind of get all messed up. I should remember there's always two secants and one tangent in every case. So the derivative of tangent is secant squared. The derivative of secant, I need another secant, so it's secant times tangent. There's always two secants and a tangent. If that helps you remember it, great. If it doesn't, forget I ever said it. All right. So let's do this one. Find the equations for the lines that are tangent and normal to f of x is equal to tangent of x over x at x equals 2. You can use your calculator. I can use my calculator? Nice. Support your answer graphically. All right. So the first thing I want to do is, in order to write the equation of a line, I need two things. I need a point, I need a slope. I've got the x-coordinate of the point, but I don't have the y-coordinate. So this is going to be y is equal to the tangent of 2 over 2. I haven't the slightest idea what that is. So I'm going to go to my calculator and go, hey, calculator, what's the tangent of 2 divided by 2? And it says it's negative 1.0925, yada, yada, yada. Remember, 3 decimal place accuracy is a minimum. If you want to give more, you can. And on this one, I probably would just go 1.0925. Now I need the slope. So the slope, well, that's just going to be the derivative evaluated at 2, right? So that's going to be f prime at 2. And don't forget, students tend to forget this because, frankly, book problems don't have enough of them in it. They tend to forget that you can do this with your calculator. If we go to Math 8, I want the derivative with respect to x of tangent of x over x. Evaluated at, remember that's what this little vertical bar means. Evaluated at x equals 2. And it's 3.433. I'm going to round that to 4 decimal places. So the tangent line would be y equals negative 1.0925 plus 3.4335 times x minus 2. And then the normal would be y equals negative 1.0925 minus 1 over 3.4335 times x minus 2. So it says support graphically. Let's take a look at what this is going to look like on a graph. So my y equals, I need to get rid of all this stuff. I want to have tangent of x over x. I really like to, when I'm doing these, do the vertical fraction, the horizontal fraction bar. And I'll do a zoom trig. I'm going to trace this to x is 2. All right, so this is the part that I'm looking at, is right here. Right here at this point. Okay? So let's see how we did. So now I'm going to add the tangent line, negative 1.0925 plus 3.4335 parentheses x minus 2. Let's graph that and see if it looks good. Oh yeah, that's nice. Clearly a tangent. And then I'm going to graph the normal. So negative 1.0925 minus 1 over 3.4335 times parentheses x minus 2. That looks pretty good. Okay, it looks like it's perpendicular. One of the nice things is when you do a zoom trig, it is a square viewing window. In other words, if you were to actually put the grid lines in there, your boxes would be squares. If you do a zoom standard, your boxes are rectangles because the screen is wider than it is tall. but it goes from negative 10 to 10 on the x and negative 10 to 10 on the y. And so it's distorted. And so sometimes if you're trying to look at a normal, you're like, that doesn't look like it's perpendicular to the tangent. It's because you're this is one of the things I dislike about this, that the normal view, the standard is a skewed graph. I'm like, you've been lying to people for, ages about what this graph actually looks like. You have distorted it. Shame on you, TI. Be better. That should have been something that was fixed in the very first time they updated anything, and yet it hasn't been fixed in like 30 years. All right, that's into the rant about TI calculators. They do some things really well. They really suck at some things that they should be better at. Like, they should be able to graph things like x squared plus y squared equals 5. They should graph things other than just functions. Now, they do parametric, which is great. They do polar, which is great. But they should be able to do relations. And it can't. Casio's can and have been able to for 20-odd years. Again, be better. All right. Okay, now I'm really done with the rant.